So whenever we try to solve a problem, the first important aspect is the dimensionality analysis or the MD analysis. This is the dimensionality analysis, which means that, so if we're looking, for example, if we have an expression for the potential in the most simple form, assuming that we have a point charge as a source, this is equal to kq over r. Then what we can say from here is that we can ask a question which might come up like this. So we can ask this question: what is the unit of k? Okay, what is the unit of k? And by the way, this can also be written 1 over 4 pi epsilon 0 q over r. So then this expression, potential, is equal to k q over r. We can say that this is equal to volts are equal to the unit of k times coulomb. This is the unit of charge divided by meter. Okay. So this is the unit, the dimensionality analysis of this expression, which means that the units of k, it should be equal to this. Volt is equal to, this is k, so we should have here volt. I'm adding the values here, okay? Here we have coulomb, then here we should multiply by meters. So this should be the unit of k, and here we have coulomb divided by meter. So now, once we have this expression, we can say that the units are the same on both sides of the equation, because volts here can cancel the volts, coulomb can cancel coulombs, and meter by meter. So we are good. At the same time, if you want to look at the units of the electric field, it looks like electric field is equal to volt divided by meter, and this is equal to the unit of k, which is as it was here, times coulomb divided by meter squared. So we can substitute the units of k, which we determined correctly in this expression, and we can check our units. Okay, this is very, very important, because often we might be asked the current density per unit volume, or the current density per surface area, or we might be asked about the density in a line, the density in a surface area, okay, in a thin sheet, or over the volume. So in those, whenever we do these, dimensionality analysis is fundamental. This is the first important aspect. If you do this wrong, you get 0 points, okay? So we should be able to learn, we have to learn this one as soon as possible. And to do this in the correct way. The second most important aspect is we have to check the order of magnitude, okay? So we have to check the order of the magnitude for whatever we are asked in a specific question, okay? Which means that so if you come to an exam and you might say that I don't have a calculator, we can say that at least if you don't have a calculator, just provide the order of magnitude for the question that you are being asked. For example, a traditional question you might sometimes see me asking is the following. Let's say that you have a pulse, okay? It's a pulse, and this is 0 volts, and this is 5 volts, okay? And then I ask you to produce from this single pulse, to produce 2 pulses that have a difference of 1 nanosecond, okay? Nanosecond. How can you do it? How can you do it? What you can do is that you can connect this wire to 2 wires, okay? And then what you have the same pulse, and these pulses, they click, they turn on at the same point in time. But the question is that, can you make them such that they will be delayed with respect to each other by 1 nanosecond? How can we do it? We know that all the signals travel with the speed of light, okay? So if we have 1 nanosecond delta t, so if this is equal to delta t is equal to 1 nanosecond, which is equal to what? 10 to the power minus 9 seconds, okay? Then we have the speed of light, which is 3 times 10 to the power 8. Unit is meter per second, okay? So what are these useful for? What one can do, someone can multiply these two together, the speed of light and the change in time, and let's see what the units are going to be. Speed of light c is meter per second, okay? We have this unit. And let's multiply this one with t, which is second. Do we obtain anything useful? We obtain a quantity which is measured in meters, and this is the dimensional analysis, right? Then the numbers will come up to be something like this. This is 3, 10 to the power 8. This is the numbers now, right? The units, they were correct. We multiply this by 10 to the power minus 9. What is this equal to? This is equal to 3 times 10 to the power minus 1. So this is 0.3 meters, okay? So it is 30 centimeters. So this is 30 centimeters. It's a hand, spanning of a hand is approximately 30 centimeters. But how can we make this useful for? What we can do is that we can measure 30 centimeters, okay? My hand is around, everybody's hand is in the order of 30 centimeters. So we make a wire, which is, we extend a wire, which is equal to this length. And then, so we just make this longer. And then the pulse here will be here, and this one will be here. So if we extend the wire by this much, we're going to get a pulse which is going to turn on 1 nanosecond later. Now, so this is something, we can call this one intuitive, but we can obtain this one at high precision, and we can even obtain delays in time shorter than 1 nanosecond. So you don't need a very high technology devices to produce pulses that are this far away from each other in time. Which means that what you can do is that you don't extend this wire with 30 centimeters, but you can extend it only 3 centimeters. And then the time delay that you can produce with very little pieces of hardware, you can produce a delay in time which is 1 attosecond, which is 10 to the power minus 10 seconds. But we can conclude this kind of analysis based only on the order of the magnitude without having a calculator. So if you come into an exam, you say I don't have a calculator, all of us should be able to obtain the order of magnitude correct. Okay. Then the third important aspect that we need to be careful about is to get the exact values, okay, or precise values, exact values. Now you need the calculator, but you can go to the third step. Once this is correct, and once we have also this correct, then we can use a calculator to obtain the accurate values. So here, this is the time for calculator. Okay, now let me answer another question, and this will be a multiple choice. Let's assume for a moment that we have a charge. We don't have a point charge. We don't have an electron or a proton. But let's assume for a moment we have a disk, okay? And this disk, it has a thickness, okay? It has a radius r, and in this disk with radius r, we cut out another disk. So we do grinding. Grinding, we just dig a hole here with radius a, okay? And this has a charge density sigma. The question is, find what is the potential at point P, okay? And the distance here, this is distance D, to point P. The question is, find the potential, okay? And you have to solve this problem. And the options are the following. You can have A. The potential at point P is going to be equal to, this is K sigma, K sigma R, another one is K sigma r squared. The other one is k sigma over r. Here we have k sigma over r squared. Now, can you choose any one of these four options? And you can also insert here, let me correct this one, not r squared, let's make this rd, not r squared, rd. And let me think for a moment. Can you come up with any solution in here? And sigma, this is important. Sigma in this case, let's assume, let me take this away for a moment. The sigma is a charge, let's assume that this is the charge density per unit area. So this is Q over meter squared, or you can write this on Coulomb per meter squared. This is the definition of the sigma, charge per unit area. And let's think for a moment, this is the unit of K. Okay, so here we have a multiple choice problem, A, B, C, D, and E. Choose the right one. Which one would you choose? So, in principle, it might be easy for us to have the potential of a point source because it's going to be this one, kq over r. But now it looks like the cube is not a point charge. It has an extension in space. It has a radius r. Out of this piece of material, we just take out another circle with a little radius a, and we have to find the potential at some point p. Okay, which one would you choose out of these five options? I'm going to pick from the class list. Attilio, Brendan. You can raise your hands. So you can pick. Okay, I can see the comment section. You have E. Okay, Brendan answered E. Okay, that's a good. So we have one answer here. Anyone else? You can write your answers. Everyone is. Can you write your answers in the comment section or in the chat section? So there are 32 students in the class. I want 32 answers right now. Brendan, why would you expect to be it E?
I can talk, sir.
Yes.
I substituted the value of the charge with sigma times m squared in the potential formula.
Here, right?
Yes, I substituted the charge with sigma times m squared.
That's correct, because these two, okay, and then what? And then?
And over r, yeah, okay, it must be the first, I was mistaken, it must be the first.
No, actually, it might be the first or the fifth. Both can be.
Which is the difference about R and D?
Well,
or in this case, are the same.
Okay, actually, R. Let's assume that this is a little r. Okay.
Okay.
Now, R and D in this case, Brendan, they are just two quantities which have units of meters, right?
Yes.
Things can be complex, but so actually, based on the dimension analysis, this could be a correct answer, okay? And this also can be a correct answer. But this can never be because the units don't match. Because the unit here, the potential, apparently, the potential should have the units of K. Okay, so let's write it like this. We should have the units of K. We should have the units of sigma, which is Coulomb per meter squared. Okay, so sigma stays there. We should have times meter squared. I'm just writing the units now. Divided by meter. Okay, so meter squared divided by meter. That means that we should have an answer which includes the units of K, units of sigma times meter. Now this one is never an option because we have the. Wait a second. We have the units of K, sigma, and meter squared. Okay, so this is taken out, right? Here we have the units of K times sigma divided by meter. This is also never an option. Here we have K sigma divided meter square. This is also not an option. So we have only here K sigma times meter, K sigma times meter. So most probably you could select this one and this one. And we are not discussing the numerical, the exact numerical value at all at this point. Then that would be the second option. But you could simplify your search space. Your search space you can simplify by taking out the options that would never be the correct answer. Okay, but thank you, Brandon. That was a good way to think about it. So you can always go back to the simplest form of the relationship of some quantity as a function of the other ones. You do the first analysis, and you can come down from 5 possible options to only 2. So, and we want you to be very careful with this dimension analysis a lot, because there is, I can give another example, of which we're going to talk in length in the future weeks. Another example is the following. We have I is measured with ampere. Okay, this is the unit of the current. Now we have the current density. For example, we can have a wire, where the wire made of copper. Okay, most of the wires are made of copper. They have very low resistivity and very high conductivity. And this wire of copper, it has a radius of 1 millimeter. Okay, and the current density J, it is measured in ampere per meter square. Okay, so this should be equal to current divided by area. Or we can write this again, current divided by surface area or something, or meter square, or pi r squared. Let's do it like pi r squared, where radius is 1 millimeter. Okay. So all of these are acceptable. But now, imagine for a moment that we have an aluminum foil. Okay, you have seen aluminum foils a lot. Of course, this is just a piece of paper. But what you might do is the following. You can connect an aluminum foil and the resistance of an aluminum foil is almost 0. Okay, it is like the wire. If you have a copper wire or a wire that you use in your home, you measure the resistance. It is going to be 0, effective 0. And what you can do is that you pick this aluminum foil, let's hold it this way, connect it to a battery. You go home, you take off the battery from the remote controller of the TV, and you can connect it with the aluminum foil, also in series with the resistance. The question now is, what is the current density across the aluminum foil? Okay, what is a possible measurable quantity, which can be called current density? So this is this quantity, current density. Now, the current here, so the current I, in principle, this can be written as J ds, the integral of this current density times the cross-sectional area. Now, immediately, we should look at the units. This is ampere, okay? This is ampere per meter square. This is times meter square. The units look good. But now we have the aluminum foil. What should be the unit of the current density J? Now, we have the current, which is going to flow along a specific direction. I'm going to draw it like this, okay? So this is the direction of flow of the current. Now, what is orthogonal direction? What is the dimension which is perpendicular to the flow of the current? You might want to think about this one for a moment. But in this case, this I is going to be equal to the J times dl. Okay, because the current will be distributed along this piece of paper. If this aluminum foil, it is like this, it is twice as, now, again. So imagine this is the width of the aluminum foil. I have two A4 papers that look like this. Now I take one out, I have this, okay? Then I fold this one like this, which means that I make this shorter. Most probably, I am increasing the current density that is flowing this way. But this, I fold this again, I get the aluminum foil a little thinner. What would you expect to happen with the current density that is flowing in this direction? You can do the same thing again and again. So would you expect the current density flowing here to increase? Brandon?
Yes, it should increase.
Should increase, but
no,
how should it increase?
Because there is less resistance in the wire.
Okay, you have an equivalent correct answer, but how is it going to change? Let me ask you this. I have this thickness of the aluminum foil, but then I just cut it in half, I made this half of what it was. If I made the aluminum foil from this, and let's not forget the current is flowing this way. This is the direction of the flow of the current. If I cut this one from this dimension to here, what would happen with the current density? It will increase. By what factor?
By 2 times.
That is correct. So if this is changing by a factor of 2, this means that this is a linear relationship. So whatever you have learned in linear algebra, it was called linear algebra because every parameter it was to the power 1. So it looks like if you multiply this by 4, the current density will be divided by 4. So it looks like you might have a relationship like this. The current density, if it is multiplied, so you have the current density times this dimension, it's a constant, okay? So you're gonna have this current is equal, you can also write it like this, J1L1, okay? This is equal to J2L2, where L2 is this distance, okay? So if we agree with this, if we agree that cutting in half this length, which is perpendicular to the direction of the propagation of the current, if this obeys like this, what would you expect the unit of J? So what is the current? This is ampere, right? What is it? This is equal to, we don't know what the unit of J is going to be, but what is the unit of DL? This is meters. Because we can measure this dimension in meters, and then we can fold it, we can make it half of what it was. This is still meters, but it's half, and J increases by a factor of 2. We keep cutting it down. So if this is ampere is equal to this quantity times meter, what should be the unit here?
Ampere over meter.
That's correct. So it looks like the current density, it can be described in a correct way, ampere divided by meter squared. Why? Because the current could be flowing through a wire that looks like this. So here I have 2 wires. One is red wire and black wire, and they both there's current flowing through these 2. And if we have a certain current, if we divide by this cross-sectional area that we see here, we can get this current. Sorry, this current density, which is measured in ampere per meter squared. But if the current is flowing not through a traditional wire, but through an infinitesimally thin piece of metal sheet, conductive metal sheet, then the unit of the current density is going to be different. Okay. Now, this is something that you have to be careful during the whole course regarding the dimension analysis, okay, which you should never fail. This is the first major part. If you do, and what is required in this course, you are going to get very few points if you don't show the units. If you write the numbers and they are correct, but if you don't associate the numbers with the units, you might lose a lot of points, okay? And using the units, it will always help you, okay? So even if you forget the formula, I don't have very good memory. I forget the formulas, the expressions, but I just go after the units. Once I try to fix the units, the expression will come up in a correct way, okay? Okay, so we can give another short break here.